Hi. So the next concept that we want to look at in equations and equations are irrational equations and inequations. So by irrational equations and inequations we mean a scenario in which you have an equation or an equality in which you have either cube roots present or square roots present and so on. So then we just want to look at how you deal with it. So the first simpler case that we can look at is the scenario in which you have a nth root present in the problem where n itself is an odd natural number. So for example, cube roots or fifth roots and so on. So if you have a statement of the form, if your inequality is of the form f of x raised to 1 by n is less than g of x raised to 1 by n, where n itself is an odd natural number, then what you can simply do is take an nth power on both sides. So the inequality, if the first form is equivalent to the second form, right? So if you have a cube root on both sides, you can take a cube on both sides and things like that. Similarly, if they had been fx raised to 1 by n is less than g of x, then you could have again taken an nth power on both sides, and you would have got f of x is less than g of x whole raised to n. When n happens to be an even number, then there are slight complications and there are certain things that we have to take care of, which will come back. We'll kind of look at them in some time. Let's just quickly look at some applications of this idea when n happens to be an odd value. So again, in the first question, you have two expressions on both sides, and you have both expressions are raised to the power 1 by 3. So again, as we've discussed, we can simply raise both sides to the power 3, and now this is a pretty straightforward problem. Get all the terms to one side. Now we just have to use the wavy curve method. Critical points are 1 and 3. 1 is from the denominator. So the expression will clearly be negative between 1 and 3. So that should be the answer to the first inequality. The second one is similar. So the second root, again, instead of a cube root, we have a fifth root, but the basic principle still applies. Since you have a 1 by n form where n is an odd value. So again, just simply raise both sides to the power 5. So now this is a cubic expression on the left hand side. So obviously the first thing that we'll have to do is first kind of factorize the whole thing first, for which we'll have to kind of guess one of the roots of x cubed minus 7x squared plus 36 equal to 0. So by observation, one of the roots is minus 2. So if we observe x equal to minus 2 happens to be one of the roots. So at x equal to minus 2, I'll get minus 8, minus 8, minus 20, minus 36. So x plus 2 is one of the factors, and I can find the remaining factors by synthetic division. So 1, right? So the factorization of the left hand side then is x plus 2 into x square minus 9x plus 18, and that should be greater than 0. So that is x plus 2 into the factors over here should be 6 and 3, x minus 3 into, and then again you have a form in which you have a product of 3 linear factors, so you can simply apply the wavy curve method again. So you want the expression should be positive, so that should happen between That will happen between -2 to 3 and then from 6 to infinity. Right, so again, if you have an equation or an inequality in which both sides are raised to the power 1 by n, where n is an odd natural number, you can simply raise both sides to the power n. Now, when you have radical signs on both sides, in which, if you have a radical sign of the form 1 by n where n is an even number, then there are certain things that we'll have to be careful about. So before getting into a more generalized form, let's first talk about the square root. Let's first essentially focus on inequalities or equations in which square roots are present, right? So we just want to look at the things that we have to be careful of when dealing with square roots which are present in an equation or inequality. So let's look at the root of x term in detail. So when we talk about the square root function f of x equal to root of x, there are two basic, the two most important things that we have to take care of are as follows. The first idea is that root of x will not be defined for all possible real values of x. Since typically when we are solving an equations and inequalities, we are talking about solution sets which are real values. We are talking about solution sets which are subsets of the set of real numbers. We always want that any quantity involved in the equation or inequality should be defined. That's why from previous examples we've seen that if you have an expression in the denominator, it should not be 0. Similarly, if you have an exponential term, you shouldn't get a 0 raised to 0 form. Now similarly, when you have square root terms present, we will always ensure that the expression inside the square root must be greater than or equal to 0. So the first important thing is that this function root of x right? So for any square root term to be defined, of course, this is assuming that you're talking about you want everything to be real. I mean, the values involved should be defined. So whenever you have a square root term present in an equation or inequality, we will always say that the expression inside the square root must be greater than or equal to 0, right? Even before we start actually solving the inequality, the expression inside the square root must be greater than or equal to 0. So as a habit, what we will always do is that if we ever have an equation or inequality in which there is a term or multiple terms containing square roots, or any other nth root where n is an even value, whether it's a fourth root or a sixth root or so on, the idea is applicable to all of them. So whenever you have a term which contains a nth root where n is an even value, then you will always impose the condition that the expression inside that square root or fourth root has to be greater than or equal to 0 to ensure that real values are involved, right? So if there is a root of f of x term, you will first find the set, impose a condition that f of x has to be greater than or equal to 0. So when you do that for all the different terms present, the set of such values of x for which these conditions are true will form a part of what is known as the feasible region. So the feasible region in any inequality or equation will basically be the set of values of x for which the equation or inequality is defined in the first place. The feasible region will become important because whatever the final solution set that we get, we will have to ensure that that solution set is a subset of the feasible region. So as a habit, it will always be important that you first list down the feasible region and then then ensure that the final solution set is some subset of the feasible region. So let's look at an example. right? So now suppose I have this particular equation that root of 6 minus x is equal to root of x minus 8. Now there might be a tendency that you will square both sides, and if you square both sides, you'll get something like 6 minus x is equal to x minus 8. And for that, when you put x, when you kind of shift around terms, you get x is equal to 7. But x equal to 7 for us will not be an acceptable solution over here. So the first thing that we'll do is we'll first have to find the feasible region. So the first thing that we'll do is ensure that each of the quantities is defined. So 6 minus x must be greater than or equal to 0. And simultaneously x minus 8 should also be greater than or equal to 0. Again, these are the two conditions that are being imposed just to ensure that the inequality, that the terms involved in the equation happen to be defined. So 6 minus x must be greater than or equal to 0 and x minus 8 has to be greater than or equal to 0. This effectively gives our feasible region as being a null set, because obviously both the conditions cannot be true. Over here we are saying that x must be greater than less than equal to 6, and over here we are saying that x must be greater than equal to 8. So the intersection of these two sets itself is a null set. So it's turning out that the feasible region itself is a null set. So there is no value of x. Since the feasible region itself does not consist of any value of x, we don't even have to go ahead and solve the equation further. So therefore the solution of the equation should also be a null set. Right, so that was the first point that has to be taken care of. Any square root terms present in an equation on inequality, we have to ensure that the expression inside the square root happens to be greater than or equal to 0. The second and very, very important point is that the square root function or the root of x term that we define is something which will itself always be greater than or equal to 0. This is slightly confusing and you should have to be very careful of, you have to understand this completely. Whenever we use the square root, whenever we use this particular symbol, whenever we have a root of x term in an equation or inequality, we by default are referring to the non-negative square root of x, right? So as a result, suppose I have this equation. So for this equation, if I square both sides and I say that okay, x is equal to 4, that is incorrect, because for x equal to 4, the left hand side's value will actually be taken as 2 and not minus 2. You're not really saying that the number 4 only has one square root as 2. The number 4 obviously has two square roots, plus 2 and minus 2. But when we're using this specific symbol in equations and inequalities, this symbol, the root symbol, is being used to denote the non-negative square root of the value of x. If x is 0, then the output of this term, the output of the root x function will be 0 if x is 0. And for any other positive value of x, the output of root of x will be taken to be a positive value. So root of x equal to minus 2, therefore I can directly say the answer will be a null set. Similarly, if I have root of minus of x minus 1 less than minus 1. In this case, again I'll say that, again as defined, root of x minus 1, the output of this term has to be something which is greater than or equal to 0. So it obviously cannot be less than a negative number. So the answer to this should also be a null set. Root of x minus 1 greater than minus 1. If root of x minus 1 is greater than minus 1, then again this will be true, since root of x minus 1 is defined as the non-negative square root of x minus 1. The output of this term is greater than or equal to 0. So obviously it will always be greater than minus 1. But now you cannot say that the answer is all real numbers, because as we discussed, the first thing that you have to ensure is that the square root is defined. So the first thing you will say is that x minus 1 has to be greater than or equal to 0. And after this, of course, what we can say is that for all such values of x which are greater than or equal to 1, this will give you a value by definition which is greater than or equal to 0, and therefore the inequality must be satisfied. Okay, so for all values of x greater than or equal to 1, root of x minus 1 itself will definitely be greater than minus 1 as per definition. Right? So this is a slightly tricky concept and it's important to understand it. So the root of x term will always be something which is greater than or equal to 0. The output of such a term will always be greater than or equal to 0. Right, so let's take another example. Suppose this is the inequality. Root x minus 1 is greater than root of 2 minus x. So again, the first thing that we want to do is go to the feasible region. So the feasible region turns out to be the set of values between 1 and 2, that's one thing. And now the second thing is, what we can do is that since by definition root of x is greater than equal to 0, you have an inequality in which both the sides are non-negative, and therefore I can square both sides without and not worry that the solution set will change. We've already seen this. If you have any inequality in which both sides happen to be non-negative, you can square both sides and the solution set will remain the same. So squaring both sides gives me, right, so squaring both sides gives me that x must be greater than 3 by 2, and now I'll have to take an intersection of 1 and 2 obviously. So my answer will be that x will belong to the set 3 by 2 to 2. So a couple of things that we can now observe, that we now have to notice that first of all, this result, that root of x square will always be taken as mod of x when you're solving equations or inequalities. This is very, very important, and it is something on which sometimes a lot of tricky questions are made. Right? So whenever you have a root of x square term, it will always necessarily be taken as mod of x. And the reason is, from what we discussed, root of some expression is a value which will always be greater than or equal to 0. So if you say that root of x square is only equal to x, then for x equal to minus 2, root of x square equal to x will clearly not be allowed, given the definition that root of x is always greater than or equal to 0 for all non-negative values of x. Root of x square equal to x will clearly not be valid when x is a negative value, and therefore to kind of ensure that the right hand side is always greater than or equal to 0, you put a mod, right? So root of x square again will always be taken as mod of x. So as an example, if I want to solve this question, I could simply say that this is root of right. So for this particular equation, I can kind of follow these steps. Again, at this stage, it is important to say that root of x minus 2 whole square will be mod of x minus 2. If you simply take an x minus 2, you get an incomplete solution set in which you will say that x is only 0, but x can be 4 also. And one thing that we can do again is we can come up with solution sets for some very simple equations and inequalities involving root of x. Again, a over here for the timing, let's assume it is some fixed, it's some number which might be positive or negative. So if root of x is equal to a and a is positive, then anyway both sides are positive, so I can square. So x will turn out to be a square. And if a is negative, for example, if root of x is equal to minus 2, then again by definition root of x has to be greater than or equal to 0. So it cannot be equal to a negative value. So x will belong to the null set. For root of x less than a, again, since both sides are positive, I can square. So x is less than a square, but x less than a square is incomplete, is actually wrong. At the same time, root of x has to be defined for which it has to be greater than or equal to 0. Right, so root of x less than a square, less than a where a is positive will have the solution set. x greater than equal to 0 and less than a square. And similarly, if a is a negative value, root of x, for example, if root of x is less than -2, that cannot happen, since by definition, again, root of x has to be greater than equal to 0. So null set. Root of x greater than a, x has to be greater than, you can square both sides, since both sides are positive, if a is positive, so x is greater than a square, which automatically also ensures that root of x is defined. For root of x to be defined, again, x had to be greater than or equal to 0. So effectively, the solution set is x greater than a square. And for a negative, root of x greater than -2, all values of x, as long as root of x is defined in the first place. So, which will happen from 0 to infinity. Right, so let's look at these problems. In the first problem, again, we can straight away say that the answer is a null set, because again, square root of some expression equal to -5 cannot be possible, because by definition it should have been greater than or equal to 0. So the first answer should definitely be a null set. Now in the second problem, there are square roots involved, so we'll first have to ensure the feasible region. So for the feasible region, what are the conditions? X minus 2 greater than equal to 0, 4 minus x greater than equal to 0, and 6 minus x greater than equal to 0. So that will effectively give us the condition that so in the second question, we'll effectively get these set of values that x can lie between 2 and 4. That's the feasible region. And now, by definition, since the square roots are anyway greater than equal to 0, both sides are positive, so I can square. Now actually at the second stage we should have also imposed the condition that this part must be greater than equal to 0. But that will actually be taken care of because x is less than equal to 4. Since x is anyway less than equal to 4, 4 minus x must be greater than equal to 0. So I can now square both sides. So that gives me a common factor of 4 minus x, so either that can be 0 or right, so I get two possible values of x, 4 and 12 by 5. But then it is important to ensure we have to check whether both these values, 4 or 12 by 5, we have to ensure that 4 and 12 by 5 both belong to the feasible region. We have to check which of these values belongs to the feasible region. So if we take an intersection of 1 and 3, 4 belongs to the interval and 12 by 5 also belongs to the interval. So both these solutions will then be acceptable. the third one, again, I can directly say that my answer should be a null set, because again square root of 2x minus 1 should have been a value which is greater than or equal to 0. For the fourth problem, root of 2x plus 3, as long as it's defined, will be greater than or equal to 0, and hence will also be greater than minus 2. So I just have to effectively ensure that it is defined. So the condition is that so as long as x is greater than or equal to minus 3 by 2, 2x plus 3 will be greater than or equal to 0, and therefore root of 2x plus 3 will be defined, and as long as it is defined, it will be greater than or equal to 0, and which will then automatically mean that it is greater than or equal to minus 2. For the fifth question, again, as we've seen that again both sides are by definition greater than or equal to 0, so you can kind of square them. But before that, we should talk about the feasible region. So 4x minus 3 is greater than or equal to 0, and 2x plus 5 is also greater than or equal to 0. So if we solve simultaneously, right, if I solve these equations simultaneously, I'll get the values of x to be greater than or equal to 3 by 4. And now coming back to the actual inequality, since both sides are greater than 0, equal to 0, I can square both sides. So now if I take an intersection of 1 and 2, I'll get my set as 3 by 4 to 4. Now in this question we'll have to be really very careful. The first thing that we should talk about again is the feasible region. Right? X less than or equal to 4 is definitely the set of values for which the inequality is defined, so that is one thing. Now we cannot really square both sides, because again squaring both the left hand side might be positive or negative or 0, right? So we can't just simply square both sides. Squaring is something which you can definitely do only when both sides are non-negative. So we should take multiple cases now. So suppose I take the case that x happens to be negative. So now think about it. Suppose x is a negative value. If x is a negative value, then the LHS is a negative number, and the RHS by definition is something which is greater than or equal to 0. So obviously the inequality cannot be defined. Something which is greater than or equal to 0 cannot be less than something which is less than 0. So for x less than 0, it is quite obvious by observation. We can directly say that there will not be any solution, right? So for the second case, we can now assume that x is greater than or equal to 3. Now, if x is greater than or equal to 0. If x itself is greater than or equal to 0, then I can simply now square both sides. Right, so I get my solution set as values of x which lie between minus 4 and 2. And now I'll have to take an intersection of which all sets. This is the solution set, this is the assumption under which you're solving it, so 3 should also be satisfied. And 1 is anyway corresponds to the feasible region, so it has to be satisfied. So we have to take an intersection of 1, 3 and 4. which will give you then, if I take an intersection of 1 and 3, I'll get 0 to 4. Then 0 to 4 intersected with this interval gives me 0 to 2. Sorry, the solution set of this inequality will be that x is less than equal to minus 4 or greater than equal to. Solution of, by the wavy curve method, the solution set of this inequality should be that x is less than equal to minus 4 or x takes values which are greater than or equal to 2, right? And so now again I have to take an intersection of 1, 3 and 4. So again I get 0 to 4 from here, and 0 to 4 intersected with this set will give us 2 to 4. Right, so in this question, multiple ideas are being used. So again, you have to appreciate that if you're just squared, if you've just started with this statement and you would have squared both sides, then you would have got your solution set as this: minus infinity to minus 4, union 2 to infinity. But that is the wrong answer. The final answer, when you consider the feasibility region and the idea that square root of something is always greater than or equal to 0, the final answer turns out to be that x lies between 2 and 4. The seventh question is kind of similar. So again, first thing we should talk about is the feasible region. Then again, for x plus 2, we should take these two different cases. So again, if x plus 2 is negative, which means that if x takes values which are less than minus 2, then the LHS is by definition something which is greater than or equal to 0. And the RHS becomes negative, so obviously the inequality cannot be satisfied. So no solution. Then the other case that we can take of obviously is that x takes values which are greater than or equal to minus 2, and so under this condition, of course, I can square both sides. Right, so when I square both sides and simplify, I get my solution set as this. X takes values which are less than -5 or takes values which are greater than 2. And now I'll have to take an intersection of again 1, 3 and 4. So intersection of 1 and 3 gives me greater than equal to -2, and when I take an intersection of 3 and 4, I'll get greater than 2. So this completes the concept on irrational equations and inequalities. Thanks. So we'll now look at some miscellaneous problems based on all the concepts that we've seen in equations and inequations so far. Right. So for the first question, an interesting observation again is that I can rewrite mod of x square minus 9 as mod of 9 minus x square. And I can rewrite 11 minus 3x as right. So by observation, the first equation can be rewritten in this form. And now again, if you observe closely, it's in the form mod of x1 plus x2 is equal to mod of x1 plus mod of x2, right? Mod of x1 plus x2 is equal to mod x1 plus mod x2. And we've already seen that that happens to be true as long as x1 into x2, that product has to be greater than or equal to 0. So from properties of modulus, the product x squared minus 3x plus 2 into 9 minus x square has to be greater than or equal to 0, which again now becomes a wavy curve problem. So in the wavy curve method, we had discussed that we'd like the coefficient of x in every linear factor to be positive. So let's take a -1 common. So if you multiply both sides by a -1, right, since you want it to be less than or equal to 0, so x can belong to the interval -3 to 1 union 2 to 3. And that should be the answer. Now for the second problem, we'll have to take two cases because there's a mod of x involved again. So we can take one case in which x is greater than or equal to 0 and another case in which x happens to be less than 0. So of course we can factorize the numerator and denominator. Let's apply the wavy curve method carefully. This is x minus 3 whole square. So the critical points over here are 2, 3, 5. Coefficient of x is positive. Wave 5 will cross, there's an odd power. At 3, since there's an even power, it will bounce back. And at 2, it will cross again. Right? And 3, of course, is a critical point corresponding to the numerator. So the solution set over here should be, if we want it to be greater than or equal to 0. So minus infinity to 2 union 5 to infinity. But we also need to take an intersection with 1. So from the statement set 1 and 2, I get the values of x as 0 to 2 union 5 to infinity. So this set is definitely, so these values of x are definitely part of the final solution set. A second case that we'll now have to take is that x happens to be negative. So again, if x is negative, then mod of x is minus x. I'm sorry, since the question is strictly less than 0, the previous answer should have been 0 to 2 union 5 to infinity. Since there is a strictly less than 0 over here, you will have to exclude the critical points corresponding to the numerator. So the answer for the first case should be 0 to 2 union 5 to infinity. So the wave at the critical point 3, the wave will bounce back. There's an even power. You'll cross at -2, you'll cross at -5. So positive, positive, negative, positive. You want the expression to be negative. So that will happen when x lies between -5 and -2. And you'll have to take an intersection of 3 and 4. So from 3, 4. So if we take a union of the solution sets of both the cases, I'll get x as belonging to -5 to -2 union. So that will be my complete solution set. -5 to -2 union 0 to 2 union 5 to infinity. The third problem is a simple application of the wavy curve method again. So let's quickly look at it. So again, 4 linear factors, coefficient of x in each linear factor is positive, plot those values. So, and of course for 0, minus half. So we want the expression to be positive, so that'll happen between so this should be the complete solution set. X can be less than -1. It can lie between -half or 0 and 0, or it could be greater than half. The fourth problem is an interesting one. It's been given that there's a certain inequality which again holds true for all values of x, for all x belonging to R, and there is a certain parameter k involved, and you want to be able to find out the values of k for which something like this will hold true. So as first step, what I could say is that x square plus kx plus 1 upon x square plus x plus 1, that entire expression should obviously then lie between minus 3 and 3. Now x square plus x plus 1 again will always be positive because the d value is negative, coefficient of x square is positive, so when cross multiply it by it on both sides. Right? Since x square plus x plus 1 was always positive, I have been able to cross multiply through it everywhere. The next step now will be important. After this, what is the essential condition that we can impose? Right? So just take a minute and think about it. So there are basically two inequalities over here, 1 less than 2, 2 less than 3, right? And the key word over here is for all x belonging to R. So you have inequalities which are holding true for every value of x. So if I consider this the 1 less than 2 inequality, and I take all the terms to one side, I get this. And again, now the key word is that this statement happens to be true for all possible values of x. But for that to happen, the coefficient of x square needs to be positive, which is the case, and the discriminant value needs to be negative. So when I impose a condition that the b square minus 4ac value in this quadratic inequality should be negative, I get these set of values of k. That k should take a value between minus 11 and 5. Of course, this is not the final answer. K lying between minus 11 to 5 just ensures that this first expression is less than the second expression for all possible values of x. Right? We similarly will now try to impose a condition on these two expressions. Again, what is important to note is that this expression is positive for all possible values of x, and therefore again the discriminant value must be negative. This will be k minus 3 whole square minus 4 square. So k minus 3 minus 4, k minus 7, k minus 3 plus 4, k plus 1. Right, so this gives me the second possible set of values of k, and now I'll have to take an intersection. So the first set was values of k between minus 11 and 5, and these are values between minus 1 and 7. So the intersection will obviously give you minus 1 to 5. From so the final answer is that k can take values between minus 1 and 5. So this again is an interesting problem. We have three expressions, three values, a square plus 2a, 2a plus 3, and a square plus 3a plus 8. And we want to consider those values of a for which these can possibly be for which these three values can possibly represent the sides of a triangle. So just think about this question for a minute. How can you come up with certain, obviously some kind of conditions and inequalities will have to be imposed, but how do we come up with those conditions? So we'll basically be imposing the basic triangle inequalities, that the basic triangle inequality that, for in a triangle the sum of two sides will always be greater than the third side. So essentially that means that right, so again the condition that we're imposing is that the sum of any two sides has to necessarily be greater than the third side. So let's solve each inequality one by one. So the first one, when we simplify, a square of course gets cancelled out. So you have 4a minus 3a, so that's a square of 5. So that's the first condition that we're getting, that the set of values of a must be greater than 5, 4a minus 3a. If we look at the second inequality, again a square gets cancelled out, 2a gets cancelled out. So we get that 3a So the solution of the second inequality gives us that a should take values which are greater than minus 11 by 3. And the third condition now gives us a quadratic inequality. So 2a square plus 3a plus 5 is positive. So again factorizing is a So this is actually turning out to be true for all real values of a, because again as you can observe, the discriminant value over here is negative. So right, and so finally since all the three conditions must be true, we just need to take an intersection of the three sets. So 1, the three statements together will ensure the set of values becomes that. Right, so taking an intersection of the three sets, we get that A has to belong to the interval 5 to infinity. So we have till now in the chapter of equations and inequalities, equations and inequations, we started by looking at the wavy curve method, and we saw that how that can be used to solve a number of inequalities in which you have a rational function on one side and maybe 0 on the other side along with some sign of inequality. Then we went on to introduce the concept of a modulus, and we've seen the different properties of modulus and the different techniques and things that have to be taken care of when you're solving modulus based equations and inequalities. We also introduced the idea of exponential based equations and inequalities. And finally, we also went on to the idea of solving irrational equations and inequalities. And we've specifically seen that if you have radical signs of the form 1 by n, where n is even, square roots, fourth roots, then there are certain things that you have to take care of. Whereas if you have radical signs of the form 1 by n, where n is odd, so for example, third, 1 by 3, 1 by 5, things like that, you can simply raise both sides to that corresponding power and reduce it to a simpler form. Thanks.